there is this really persistent headache in the world of large language models.
Oh, yeah, the impossible triangle.
Right, exactly. It's the ultimate have your cake and eat it too problem for engineers.
Yeah.
Basically, we all want our AI models to be smarter.
Which usually means making them massive.
Right, adding billions and billions of parameters.
Yeah.
But at the same time, we want them to be fast, and we definitely, absolutely want them to be cheap to run.
Which contradicts the massive size.
Exactly.
Yeah.
The rule of thumb has always been you pick two. You just can't have it all.
It makes sense intuitively, right? I mean, if you want it smart and fast, you need incredible hardware, so it's going to cost an absolute fortune.
Yeah.
And if you want it cheap and fast, you have to cut the brain size down, so it's just not going to be very smart.
Exactly. Or, well, at least that was the rule. But today, we are doing a deep dive into a paper that basically looks at that triangle and says, actually, I think I'll take all three.
It's a massive claim.
It is. We are unpacking DeepSeek-V2 today. So for those of you listening, this is a major release from DeepSeek AI.
The paper is called DeepSeek-V2, a strong, economical, and efficient mixture of experts' language model. And I really want to emphasize that word economical here.
Yeah, they aren't just talking about saving a few pennies.
Not at all.
The stats in the abstract are honestly a bit startling. They claim they can save 42.5% on training costs and boost generation speed by nearly 6 times compared to their previous model.
Which is huge.
Right. And they claim to do all of this while trading blows with absolute heavyweights like LMA370B.
It is a bold claim. And, usually when I see efficiency jumps that drastic, I immediately assume they cut corners on the intelligence side.
Right, the catch.
Yeah, there's always a catch. But the architecture here suggests they actually found a way to cheat the system, or at least totally rewrite the rules of how the system allocates its brain power.
Well, let's start with the sheer scale of the thing, because that's where the contradiction really hits you. We're looking at 236 billion total parameters.
It's a monster.
It is massive. That is firmly in supercomputer territory.
It really is.
But then you look at the fine print, and it says only 21 billion are active for any given token.
Yeah.
So help us bridge that gap. How do you have a 236 billion parameter model that only uses, less than 10% of its brain at a time?
So this is the core of the mixture of experts architecture, or MoE. To really get why DeepSeek-V2 is special here, we should probably contrast it with a traditional dense model first.
Okay, lay it out for us.
Think of a dense model like the original GPT-3 or early Llama models as a general practitioner doctor. No matter what problem you walk into a clinic with, whether it's a broken leg, a heart condition, or just a cold, that one doctor tries to use their entire medical education to treat you.
Every single neuron fires for every single request.
Exactly, which is highly inefficient.
Because you don't need to recall a cardiology textbook to fix a broken toe.
Precisely. It's a massive waste of energy. Now, a mixture of experts model and MoE is more like a massive, highly specialized hospital.
Okay.
You have specialists for everything: cardiology, neurology, podiatry. When you walk in with that broken toe, the hospital doesn't wake up the brain surgeon. They route you directly to the podiatrist.
I see. So the 236 billion is the total staff of the hospital.
Right.
But the 21 billion is just the specific team actually treating me in that exact moment.
Correct. You are only paying the compute cost for the active experts, not the whole building. But here is where DeepSeek-V2 really changes the game. Traditional MoE models usually just have a few very large experts.
Like broad strokes.
Yeah, maybe you have a science expert and a literature expert. But DeepSeek went for extreme granularity. They call it DeepSeekMoE.
DeepSeekMoE, right.
Instead of a few big experts, they segment the model into tiny, highly specific experts.
So instead of a generic, food expert, you'd have a pizza expert, a sushi expert, and a tacos expert.
Even more specific than that. Maybe a dough fermentation expert and a spicy salsa expert.
Oh, okay.
By breaking it down this small, the model can be incredibly precise about which exact neurons it activates. But there is an inherent risk with this approach.
I can actually see that. Because if you fragment the knowledge too much, don't you lose the big picture? Like if the cheese expert refuses to talk to the dough expert, you can't make a pizza.
That is exactly the problem. That and redundancy. Regardless of whether we are talking about pizza or astrophysics, you still need basic language skills.
Right.
You need to know what the word "the" means or how to structure a sentence with a verb and a noun. If every single tiny expert has to learn sentence structure from scratch, you are wasting massive amounts of parameter space.
You're just duplicating the basics 1,000 times over.
Exactly. So DeepSeek introduced something called shared expert isolation.
Okay, how does that work?
Imagine you have a team of generalists who are always active. They handle the syntax, the common context, the basic logic that applies to literally everything. They form the foundation.
Okay.
Then you have the routed experts, the specialists we talked about, who are only called in when specifically needed.
So for every single word generated, those generalists are always in the room, and they just tag in the specific specialist required for that millisecond.
Yes. And this allows the routed experts to focus purely on their tiny niche without needing to be well-rounded at all. It is a very, very efficient division of labor.
That makes a lot of sense. But doesn't this create a nightmare of a traffic control problem? If you have thousands of tiny experts, just deciding who gets the ball must take a toll.
It does, and it's not just a software problem, it's actually a physical hardware problem. This brings us to device-limited routing.
Yeah, this part of the paper got pretty technical. It sounded like they were really worried about the actual physical location of the data on the silicon chips.
They absolutely are. When you train a model this huge, it doesn't fit on one GPU card. It's spread across massive clusters of them, basically a whole room full of servers.
Right, just racks and racks of chips.
Now, inside a single chip, data moves at lightning speed. But moving data between chips over the network, that is painfully slow. It's known as communication overhead.
Okay.
If your routing algorithm picks 3 experts to handle a token, and they happen to live on 3 different GPUs on opposite sides of the room, you have to ship that data across the wires, which completely kills your training speed.
So you really want to pick experts that live close to each other.
Or at least limit how many different houses you have to visit, so to speak. DeepSeek-V2's routing mechanism intentionally limits the target experts for each token to, at most, 3 devices.
It's like saying you can consult any expert you want as long as they are all in this specific building. Don't go driving across town.
That's a great way to put it. It forces the router to be geographically smart about where it sends data, and to make sure this doesn't result in one super expert doing all the work while the others just slack off. They use auxiliary losses.
Auxiliary losses.
Think of it as a mathematical penalty or a tax during the training process.
Yeah.
If the router keeps sending work to the same expert over and over again, the system mathematically penalizes it.
Oh, interesting.
It forces the router to spread the workload evenly across all the available experts and devices.
Forced collaboration. I like it.
Yeah.
So that really explains the training efficiency and those massive cost savings.
Yeah.
But we need to talk about inference speed now, the actual speed at which it talks back to us as users. Because you mentioned a 6x boost earlier.
I did.
And you don't get a 6-time speed up just by organizing your experts a little better.
No, you certainly don't. That speed boost and the massive context window they achieved comes from a completely different innovation in this paper, something called MLA, or multi-head latent attention.
Okay, I definitely highlighted this section in my notes, the bottleneck breaker. This is addressing the KV cache problem, right?
Correct. To really understand why MLA is such a huge deal, we have to look at what usually slows these large language models down. When you are chatting with a model, it has to remember the context of the entire conversation.
Right. The chat history. Everything I said 5-10 minutes ago.
Exactly. Technically, it stores this in what's called a key value cache, or KV cache. For every single token it generates, it has to look back at the keys and values of everything that came before it, just to decide what word to say next.
Right.
As your conversation gets longer, that cache grows linearly.
So it's kind of like trying to have a conversation while carrying a backpack, and someone drops a new rock in the backpack with every single word you speak.
That is a perfect analogy. Eventually, that backpack is so heavy you literally can't move forward. The memory bandwidth gets completely choked, and the model slows to a crawl. This is the main reason why running long context models is historically so expensive and so slow.
So how does DeepSeek-V2 lighten the load? What's their trick?
Well, previous attempts used tricks like multi-query attention, MQA, or grouped query attention, GQA. Basically, they tried to simplify the memory by grouping things together.
But there's a catch with those, right?
Always a catch. You lose detail, you sacrifice a noticeable bit of performance just to gain some speed.
And DeepSeek wasn't willing to make that trade-off.
No, they took a totally different approach. MLA uses low-ranked key-value joint compression.
Okay, we definitely need to de-jargon that for everyone listening. Low-rank compression.
Imagine you have a massive, ultra-high-resolution photograph of every single interaction in your conversation. That takes up a massive amount of space.
Right.
MLA essentially converts that heavy photo into a highly efficient vector sketch, a latent vector. It projects all that heavy key-value data into a much, much smaller, compressed format.
How much smaller are we actually talking about here?
The paper claims it reduces the KV cache size by 93.3% compared to their previous 67B model.
93%. That
Yeah.
sounds impossible. If you compress a file that much, usually it just turns into pixelated garbage. You lose all the nuance.
That was the initial skepticism in the community too, but they claim the performance remains comparable to standard uncompressed attention. However, there was one major hurdle they had to clear to make this actually work, and that is ROPE.
ROPE. Okay, that stands for Rotary Position Embedding. This is basically how the model knows that the phrase man bites dog is fundamentally different from dog bites man, right? It's the word order.
Exactly. Position is everything in language.
Yeah.
The problem is standard ROPE is very sensitive. If you try to compress the keys and values down into this tiny latent vector sketch we just talked about, the positional information gets completely scrambled.
Oh, I see.
You lose the map of where the words actually belong.
So you have this nicely compressed memory, but you have no idea which word came first. That's entirely useless.
Right. So DeepSeek used a decoupled ROPE strategy. They said, okay, we will compress the content, the actual meaning down to a tiny size, but we will keep the positional data completely separate.
They split the signal.
Yes. They have a dedicated uncompressed channel just for the positional embeddings. It's lightweight because position data inherently isn't huge, but it needs to be precise.
That is incredibly clever. So the heavy stuff gets crushed down, but the map stays high resolution, so the model never gets lost.
Precisely. And that right there is how they achieve that 5.76 times generation speed and how they can easily support a context window of 128,000 tokens. They solved the memory bottleneck without losing the map.
All right, so we've got the brain structure sorted with MoE, and we've got the photographic memory with MLA. Let's pivot and talk about what this brain actually studied, the training data.
8.1 trillion tokens.
Which is just a staggering amount of reading.
It really is. Now, for some context, LaME 3 was trained on about 15 trillion, so DeepSeek is a bit lighter, but 8 trillion is still a massive corpus. The composition of that data is what's really interesting here, though.
Right.
Being a Chinese lab, they included significantly more Chinese language data than typical Western models do.
That makes perfect sense.
Yeah.
But I also noticed a specific note in the paper about their data filtering process. They deliberately removed contentious content.
They did. They explicitly filtered out data they deemed controversial in order to create a more neutral-based model. But this had a fascinating side effect when they finally ran the benchmark tests, specifically the MMLU.
MMLU, right, that's the massive test covering everything from high school history to advanced physics. I saw that DeepSeek-V2 performed slightly worse on a specific subset called humanity moral.
Right. And here is where we clearly see the technical impact of data curation. The humanity moral subset of the MMLU is largely based on Western and very specifically American cultural norms and values.
Okay, so a specific worldview.
Yes. So by scrubbing their training data of contentious topics, which naturally likely included specific regional cultural stances, they effectively removed the underlying data that aligns with the correct answers on that specific American test.
Okay, I want to make sure I have this right. It's not that the model somehow lost its morals. It's just that the training data no longer mapped perfectly to the test data.
Exactly. It's just a data distribution mismatch. If you remove a specific culture from the training, you will naturally fail the test based on that culture. It's a very clear example for us of how performance on these big benchmarks is often just a measure of how well your training data matches the test creator's worldview.
That is a really important distinction to keep in mind whenever we look at these leaderboards.
Yeah.
Now, another thing that stood out to me in the training section, they didn't use SFT during pre-training.
Right. So supervised fine-tuning, some recent models like Mini CPM, for example, inject SFT data, basically structured Q&A pairs right into the early pre-training phase to kind of give the model a head start.
But DeepSeek didn't do that.
No, they kept it pure. Pre-training was strictly raw, unsupervised learning. They saved all the SFT for the alignment phase later on.
Which brings us perfectly to alignment. This is the phase where they actually teach the model to be a helpful assistant rather than just a really good text completion engine. And they use reinforcement learning here.
Specifically, they used Group Relative Policy Optimization, or GRPO.
Okay, another acronym to unpack. Why do we need GRPO? What was wrong with the old way of doing things?
Well, in traditional reinforcement learning, something like PPO, Proximal Policy Optimization, you usually have to run a critic model. The critic is a whole separate neural network, often just as big as the main model, and its only job is to look at what the main model generates and give it a score.
Like grading a test.
Exactly. It says, good job, that was helpful, or bad job, that was complete gibberish.
But that means you're running two giant models at the exact same time, the actor and the critic.
Yes, and that basically doubles your memory and compute costs right there. It's insanely expensive. GRPO gets rid of the critic model entirely.
Okay, but how do you grade the homework without a teacher?
You use peer review, or rather group comparison. GRPO generates a group of outputs for the exact same prompt, let's say, 5 different answers, and then it simply compares them against each other to estimate a baseline. It scores the best answer in the group higher than the worst one in that group.
So it grades on a curve, essentially.
In a way, yes. And it saves a massive amount of hardware resources. But even with this highly efficient training setup, they still ran into what they call the alignment tax.
The alignment tax. This sounds like something every single model builder has to pay eventually.
It is a huge recurring theme in AI research right now. DeepSeek found that as they used reinforcement learning to optimize for helpfulness and safety, making the model polite, making sure it strictly follows instructions, the performance on raw, hard logic tasks actually dropped slightly.
Specifically on the BBH benchmark, right? Big bench hard.
Correct.
So just by teaching the model to be nice, we inadvertently made it slightly less smart.
Or at least less rigorous. Think about it, when a model is constantly checking its own internal safety filters and trying to perfectly align with human conversational preference, it restricts its own solution space.
Right.
It might second-guess a complex logical leap simply because the phrasing conflicts with the politeness rule it learned.
That is the tax. We pay for safety with raw intelligence.
Exactly. Now, DeepSeek mitigated this by using a two-stage strategy. First, they trained it purely on reasoning math and code, areas where there is only a right or wrong answer. No politeness needed.
It was raw logic.
Right. And then, only in stage 2, did they add the human preference alignment.
Get the logic rock solid first, then teach it some manners.
Exactly.
So let's look at the scoreboard now. Does this highly elaborate architecture actually pay off against the giants currently dominating the space?
It absolutely does. And keep in mind, we are comparing a model with just 21 billion active parameters against dense models that are significantly larger.
So how does it fare against LaME 370B? Because that's the open source benchmark everyone is watching right now.
It is highly comparable. In math and code benchmarks, things like GSM-8K and Human Eval, DeepSeek-V2 is right there going toe-to-toe with LaME 370B. And unsurprising given its training data, it absolutely crushes LaME on Chinese language tasks.
And what about other MoE models? Mixtral 8x22B is probably the big open source competitor in that specific category.
DeepSeek-V2 comfortably claims the crown for the strongest open-source MoE right now. It beats Mixtral on the MMLU benchmark and across most English tasks.
Were there any exceptions?
The only place Mixtral held a slight edge was in a few common-sense trivia tasks, like Trivia QA.
But for hard skills coding and math, DeepSeek seems to have the clear edge.
Definitely in coding. They heavily highlighted the Live Code Bench results in the paper, and this is important because Live Code Bench tests the model on coding problems that were released after the model's training cutoff date.
Oh, so it physically can't cheat by just memorizing the answers from a GitHub repo somewhere.
Exactly. It has to actually understand the code, and DeepSeek-V2 achieves a very high pass at 1 score there.
And for those unfamiliar, pass at 1 means getting the code entirely right on the very first try, correct?
Yes. And if you're a software developer using this as a coding assistant, that is really the only metric that matters. You don't want to spend an hour debugging the AI's code. You want it right the first time.
They also briefly mentioned a light version of the model in the paper.
Yes, DeepSeek-V2 Lite. This is actually super fascinating for the hobbyists and smaller developers out there. It has 15.7 billion total parameters, but it only activates 2.4 billion per token.
2.4 billion active. That is tiny. You could run that locally on a high-end consumer graphics card in a gaming laptop.
You absolutely could. And because it utilizes that exact same MLA architecture we discussed, it still has that massive context window and runs incredibly fast. It literally brings this high-efficiency enterprise tech down to the consumer desktop level.
So zooming out for a second, what is the core mission statement here? What does DeepSeek-V2 really prove to the wider AI industry?
I think it proves that the brute force era of AI might actually be ending. For a long time, the dominant strategy was just add more parameters, buy more GPUs, burn more electricity.
Brute force.
Right. DeepSeek V2 shows that architectural innovation, specifically this highly granular mixture of experts combined with the memory compression of MLA, is a completely viable and much cheaper alternative.
Works smarter, not just harder.
Exactly. They achieve top-tier performance at a fraction of the traditional training cost. This democratizes high-end AI in a big way. You don't need a Google-sized budget to train or run these massive systems if you design them intelligently from the ground up.
And the paper explicitly mentions they aren't stopping here.
No, they state their next goal is hitting full GPT-4 level performance and moving into true multimodality. They want this efficient architecture to handle images, audio, and video natively, not just text.
Man, if they can apply this kind of insane efficiency to a true GPT-4 class multimodal system, that is going to shake up the leaderboard significantly.
It certainly will. It's a space we have to watch closely.
But before we wrap up today, I want to leave the listener with that thought we discussed about the alignment tax. It's the part of this deep dive that is really going to stick with me.
It is arguably the essential philosophical question for the next few years of AI development.
Because if making a model safe and aligned inherently puts a ceiling on its raw intelligence, are we optimizing for the right things? Obviously, we want AGI to be brilliant, but we also want it to be nice and safe. DeepSeek V2 shows us that a balance is possible, but there is still a tangible cost.
It suggests that raw intelligence and human preference might actually be orthogonal vectors in some ways. As we push these models further into the unknown, balancing that raw reasoning capability with human-centric safety is going to be the defining challenge for researchers.
A heavy thought to end on, for sure. DeepSeek V2 is a massive technical marvel, but it also opens up some really fascinating questions about how we build the future of AI. Thanks to everyone for listening to this deep dive.
See you next time.